This part of the course is known as the equations of motion, or the SUVAT questions. It gets its name from the 5 different variables that it involves. S represents the displacement of an object, U is its initial speed, V is the final speed, A is for acceleration, and T is the time taken for the motion to happen. There are 5 variables here, and there are 5 different versions of the equation. Each of the equation is missing exactly one of the variables, so you have to be quite careful about choosing which one. This applies in one-dimensional motion in X, also in Y, and finally these equations are used in two-dimensional motion when we're trying to work out the path of a projectile, something like a bouncing ball here. The reason we call them the SUVAT equations is because it's actually quite challenging to recognize sometimes exactly what information you do have and what information you don't. So across the country, students are encouraged to follow a certain procedure that allows them to maximize their chances of getting this process right. So each time what we do is we write down the acronym SUVAT, usually in a vertical list. We write in what values we know and note what we're after, typically with a question mark. You then consult your memory or your equation list and you try and figure out which one of these 5 equations it has what you need as well as what you have and does not have any variables that you're not interested in. Once you've got that, you carry on as usual. So here are 3 examples. I'll show you each of them as part of this presentation, and then there'll be some other ones for you to practice with later. Just to get stuck in with what we already know, let's take a look at this first question. So we know there's a car traveling at 10 meters per second, and then it accelerates, and we know the rate of acceleration is 2 meters per second. The question's asking us, how long does it take for the car to get up to a speed of 25 meters per second? So what we do is we write down SUVAT. We then identify what information we know. So we know that the initial speed was 10. We know the final speed we're after is 25. The rate of acceleration was 2. And it is the time that we're after. This gives us 4 out of 5 of these variables. Consulting our list, what we need to do is figure out basically which one doesn't have S in it. And that's this first one. We've chosen this as your starter example because that equation is the only one out of the 5 that is familiar from National 5. It's basically the definition of acceleration rearranged. So we take that equation, we then write it down, substitute in each of our numbers, do a little bit of algebra sometimes. Here we're going to subtract 10 from both sides. 25 take away 10 makes 15, 10 take away 10 makes 0. Finally, we divide both sides by 2, and 15 over 2 is 7.5 seconds. Now you might say, well, last year I could have done that question as well, and I didn't need this fancy SUVAT thing that you're telling me about. And you're right, it is exactly the same as the National 5 example. The reason I'm going out of my way to encourage you to use this method is because at higher, it often really is not so clear exactly which equation you ought to be using. For example, you might do sums involving conservation of momentum, conservation of energy, the area under graphs, as well as a whole bunch of other things. So anytime you see these type of variables, just automatically write this down and then spend a little bit of time just purely thinking, do I have this? Do I have that? Do I have the next one? And that forces you psychologically to actually engage with the written text, which is a big lifesaver for many, many pupils. So before looking at the other examples, I need to actually show you or convince you that this stuff is actually true. It's not really the way we work in physics to just take an equation out of nowhere, tell you it's true, ask you to trust me, and then do a bunch of work on it. Sometimes we'll show you the equation comes from a mathematical observation. We might deduce something from our classroom observations. Other times we might try and prove it. We might do experiments. And ideally, we would always do both of those things for every single situation. Sometimes that can be quite difficult, particularly when we're working remotely, but there are experimental proofs of most of these things as well. But what I'm going to show you now for each of these new equations is the mathematical derivation. These can be quite tricky for students to follow because they don't necessarily see why I'm choosing the path that I'm choosing, or they get overwhelmed or intimidated by what's going on. Bear in mind that you don't actually need to reproduce any of this in the exam. The reason we're including it is to basically show you that we're willing to put our money where our mouth is and that there are reasons behind the equations that we've got. I'm not expecting you to take this on faith. But anyway, for our first equation, we're going to start with the definition of acceleration. Acceleration, the word in physics, means how quickly your speed is changing. So how much your speed has changed for each unit of time. In other words, an acceleration of 5 means that your speed is going to go up by 5 meters per second every individual second. This triangle shape is called delta, just like in E is mc delta t, and it just means change. This is technically called a calculus notation, and you'll meet that in maths this year quite a bit. The second line here just separates out a little bit. Instead of saying change in time, we just say time, because, well, it's largely the same thing. And instead of change in v, change in speed, we're going to specify it a little more. V is representing the final speed, u the initial speed. And v take u is the same as change in speed. After that, we multiply both sides by t, so that goes over there. And then we get this line if we turn it around. And finally, just for convention, add u to both sides so that it goes over onto the right. This is the equation you end up with. For equation number 2, we want to have a look at the displacement rule for a speed-time graph. So if I have some random motion where I have a starting speed that is not 0 and I'm going to accelerate, which means my speed will increase. I'm not telling you exactly what the rate of acceleration is, but as long as it's consistent, everything here follows. I should say that for all the SUVAT questions, it is only true for consistent acceleration. That might be positive, negative, or 0, but it can't be changing. So here we have a positive acceleration. Now we're going to add some extra labels. I'm going to say that the starting speed, that's that point there. Whatever that number would be on the graph, I'm going to call u. Likewise, the final speed, I'm going to call v, whatever that number corresponds to in any graph of any piece of motion you want to look at. The reason I'm not using particular numbers is for a derivation, we're trying to show this works for every possible case and not just one or two. Finally, the change in time for this graph is going to be this size along here, whatever time it took from the starting position to the final position. And the last step is to use the rule for working out displacement from this. This is from National 5, and it says displacement equals the area under this line, so this sort of section here. That is made up of two parts. Area number 1 is a rectangle, area number 2 is a triangle. Fortunately, we already know the equations for working out those areas, so we just have to work things through. Before going further though, please note that the height of this triangle is this value, take away that value, so it's v minus u. So total area, that's going to be equal to the displacement, that's equal to area 1 plus area 2. For area number 1, it's the height of the rectangle multiplied by the width of it, that's ut. And for the triangle, the area should be 1/2 times the base times the height, or 1/2 times the base, that's t, and the height, I just said, is v take away u. So that's our sum. Now I could leave it like that if I particularly wanted to. That would be true, I could use that in various sums. But that's not the endpoint I'm trying to get to. I'm trying to get s equals ut plus 1/2 at squared. So there's an extra step. And the extra step is to go back to what we had before. On the last slide we ended up with this equation here, v equals u plus at. If you go back before one step, we had this. Or indeed you can just take away u from both sides. And what this is showing is that for whatever motion you're talking about, v take away u is going to be the same as the acceleration multiplied by time. In this little bracket here, that's what I have. I have v take away u. So I'm going to trade this for that, because this equation here is saying they're the same thing. And that's what I'm doing here, this bracket for that bracket. Finally, just a bit of tidying up. S is ut, yep, sure, half, sure. And then I've got t multiplied by a multiplied by t. So it's easier to just say at squared. And that's the equation I was after. Job done. A little side note, should you have the case where the acceleration is 0, what you end up with is s equals ut, or in other words, distance equals speed times time. That's the trivial case. It's always reassuring in physics when you add on an extra bit where you can show that in the particular cases you were talking about before, the new equation also reproduces what you already know to be true. For the next one, what we want to do is take the last equation, and then I'm going to substitute in the first one. That was this one here. Then do a little bit of tidying up, really. So again, we have two options there, and I'm largely going to reverse this final sort of bit, take us back to where we started on the previous slide. So I said before, at is the same as v minus u, so I can swap it back out if I particularly want to. Next, we're going to do some algebra. So this term has a t in it, this term has a t in it. I'm going to divide everything in this equation by t, and on the left hand side I get s over t, and then on the right hand side this term loses a t, and this whole term here loses a t, producing that. After that, you need to recognize that a whole u take away half a u ends up being just half a u. Apologies, I missed a step. In this case here, you multiply out the brackets. Half times v minus u is half a v, take away half of a u. You then do full u, take away the half u, leaving you with plus half a u. Next step, well, multiply both sides by t, so the t comes back up to the top, and there you have it. You can then put the halves outside the bracket if you particularly want to as well. And this is the fourth equation. This one here, to interpret it, what it says is your distance equals, well, your average of the speed multiplied by time. So it's not really saying anything particularly shocking either. For the next one, we're going to take the first equation, square it, and then we're going to substitute with equation number 2. So here we go. Here we go. We know these. We're happy to start with them. If I'm going to square this equation, what it means is this side gets squared and all of this side gets squared. That's what this line says. You then have the FOIL rule from maths. What it says is if you have this bracket multiplied by itself, well, you multiply the firsts, so that's u times u again, because you would have two brackets. That gets you u squared. You do the outsides, which is u and at of the other one. And you do the insides, that's this at and the u of the other one, and you end up with two of them. Finally, you do the last, which is at times at, and you get this term here. Next stage, you want to take 2 and a out of these two terms. And you want to basically pull it out of the bracket to find the common factor. This first bit has a 2a already in it, so when you take out the 2 and the a, you just get left with the u and the t. For the second one, there's an a you can take out, so you lose one of them, you end up with just single a instead of a squared, but there isn't a 2. So when you divide this term by 2 in order to get one outside, you have to do this here to cancel it out. Final step, this whole bracket equals the right hand side of what we had before. So this lot is the same as s, therefore I can swap all of this for s. And I have this equation here. V squared is u squared plus 2as. The fifth one I don't really want to go into. It's mainly a side note and we don't really use it very often. You can try and derive it if you like, but I'm not going to worry too much. I have shared notes with you on how to do that though. Here is a hint if you would like a challenge. Now on to our worked examples. So we've already had a look at the first one. Let's have a look at number 2. So a car is travelling at this speed. The driver applies her brakes. There's a certain acceleration. And we want to know how far she's going to travel before coming to a stop, the so-called stopping distance. Well, we have our procedure. We write down the acronym SUVAT. And then that forces us to have a think about what it is we have and what we don't have. You see, we know this number, and sometimes people might just assume that's the final speed if they're not careful. But it's actually the initial speed. We know the acceleration, and we know another thing. This is the power of SUVAT. By forcing you to go through each of these in turn, you actually realize the implied information. So because we're told it comes to a stop, that tells us the final speed is 0. Likewise, because we're asked how far does she travel, we know we're after the displacement. We're now going to look at our list and we're trying to find an equation without time in it. Well, there's only one. It's this one down here. So that's what we use. One point to be careful on is the direction of the acceleration. It doesn't actually matter if you choose forwards or backwards to be positive or negative. The math works either way, but you have to be consistent. If we're saying forwards is plus 20, then the acceleration has to be in the backward direction, which is negative. So v squared, well, that's 0 squared, so 0. U squared is 20 squared, which becomes 400. And 2as, well, we don't know s, but we do know 2a, that's minus 4. Here, I want to subtract the minus 4 from both sides. Correction. I want to add 4 to both sides to cancel out over here and get it over there. So 0, add a 4s, gets us this. This term over here, add a 4s, cancels it out so that it disappears. We can also simplify the 20 squared to become 400. On this line, 4s is equal to 400. That means 1s will be 100. And since it's a displacement, the units must be in meters. Some people would prefer to take this line and then start applying the rules of algebra in order to work out s equals something or other before they put the numbers in. In general, at university and so on, that's usually quite a good option, and people like the simplicity of it sometimes. But the way your exams are marked means that that's actually quite a poor strategy for you. If you do that and make any mistake whatsoever, you pretty much sacrifice all your marks. Whereas if you just write down the original equation, stick in the numbers on this line, that's going to give you 2 out of 3. That's 66%. That's pretty much a B. Almost an A. All these other bits that people often get confused on don't hurt your chances. So it's really in your interest to basically write down the equation as it is on the sheet, then substitute in your numbers, and then try all the tricky stuff. It's also true that quite often in these more complex equations, if you have zeros or ones, for example here, we didn't have to worry too much about the square, because 0 squared is still 0. In this example, we have a stone being dropped down a well, and we're only told it takes 5 seconds to strike the bottom. You might think that means we're actually really struggling for data, and many people get quite confused, freak out, and just don't feel they have anything to work with. It turns out though there's quite a bit more here, and this illustrates quite nicely why the SUVAT method is so powerful. So rather than freaking out, we just proceed as normal. Have a bit of faith. So we write down SUVAT and then we go through it one by one looking for information. First thing, S, displacement. What information do we know? Well, we know that that's what we're after, so we fill in that. That's the question mark. We also know the time. That's 5 seconds. That's the only number in the question. But there are other information here as well. For example, we know that the stone is dropped. That means it's released from rest. It's not thrown up the way either. It's just released. And finally, we know it's happening on Earth. We know that, therefore, the value is equal to 9.8 for the acceleration. Here I'm saying it's negative. That's just the downwards direction. Suddenly, doesn't look so scary. If we have a look at our list of equations, we're looking for one that's not got any v's, so we have a look through, and that one will do just nicely. To solve the problem, well, just as before, we have our equations. U is 0, so ut will be 0. Half's a half, a is minus 9.8, and t squared is 5 squared. Many people write the equation and then just write down 5. That's not very good. You have to actually square it if it says to square it. Last of all, you put this into the calculator and it will come out as minus 122.5 meters. One small point is the sign convention is something we've chosen. We decided down means negative, but the person who asked the question maybe doesn't get that. So it can be a nice little bonus to write down a sentence saying the well is 122.5 meters deep, for example. To be honest though, the rounding should probably be to fewer significant figures based on the data in this question. So we've mathematically derived some equations of motion, and I've showed you a few examples of how you can use them. The bit that we would normally show you in class is then an experiment to confirm these things are actually true. One way of doing that involves using an ultrasound sensor directed across a car, and you can take information that way. That's nice for a demonstration. But the pupil experiment we normally do involves a car on a ramp with a light gate at the bottom. The variables you might investigate include the displacement from the release point to the light gate. So that allows you to control that. And what you measure is the speed. So the light gate measures the time the fin here takes to go through the gate, and from that you can work out the speed. Now the equation that links these two is this one here, v squared equals u squared plus 2as. U is going to be 0, so it doesn't matter, and a depends upon the slope of this ramp. So really it's a plot of speed squared against displacement you're going to put on the graph. If you compare these two equations and you plot them as I've described, so you plot v squared on the y-axis of the graph and you plot the displacement on the x-axis, well, comparing to the familiar y equals mx plus c, it suggests the intercept on that graph will be equal to whatever the starting speed is, in our case 0, and the gradient of your line should be equal to double the acceleration due to your ramp. This is one method you could use for working out the acceleration, but here our interest is just checking to see if this equation actually works. There's a bit on uncertainties, but I won't cover that in a video. Some example data might look like this. This is fake generated data. You can actually get far neater and nicer data from real experiments, but this is just an illustration. So we have different release positions, and based on the position of the gate, that might translate into different displacements. We measure the velocity at the gate 3 different times for each displacement and calculate an average. Once we've got our averages, we calculate the square of them, and then we're ready to make a graph. In previous work, the idea was you have your graph and it should be a straight line through the origin. You plot the data, you decide on the line of best fit, and you go, yeah, great, it actually followed what we expected. It is a straight line going roughly through the origin. Here, though, we can go a step further. We can ask here the Excel spreadsheet to work out what the equation ought to be for this blue line. And from this value here, that's the gradient, we can work out what the acceleration must have been along that ramp. So according to the theory, the gradient is equal to double the acceleration, so we take the gradient value, half it, and that gives us the acceleration on that ramp. A nice extension for the class experiment is to then change your timing box, the TSA, to the acceleration mode, and then see if you get the same value. There's also a section on the course with forces where from the angle of the ramp you can work out what the rate of acceleration ought to be. This ties in with Galileo's work as well. And there's multiple ways for getting the same thing, which allows you to compare methods. In general, the graphical method will always be superior because you're using many data points working together to get a very good result. A nice example of data might look something like this. there's actually little error bars here showing you the uncertainty around the measurements. And this is showing you that we're measuring these things very, very precisely. We're being very confident with where the points are. And still, they line very neatly up along this straight line through the origin. This tells you, in as best a way possible, that the theory really works. A second experiment, a popular one for assignments, includes measuring the acceleration on Earth. Here what you have is a little clip that holds a steel ball bearing. There it is. And you have a strike plate. This strike plate is designed so that it's sitting upright on a little catch, and when you hit it, the catch is knocked loose. Both of this and the little clip allow electricity to pass through it, and we plug those things into our TSA timing box. When you open the clip, that starts the timer, and when the ball strikes the plate, it stops the timer. This allows you to make very, very precise measurements of the time it takes for this ball to fall. To measure the height, well, you just go from roughly the plate to roughly the bottom of the ball. Having a look at the equations, well, we're looking at displacement here, and we're looking at time. So S equals ut plus a half at squared is the correct one to describe this physics. We know u is going to be 0 because we're dropping it. That's just to simplify things. So that disappears. And we know the rate of acceleration is going to be g. Here I've chosen to make it positive just to keep things simple. And we have to use a very sensitive timer on this, a very precise one, because the values are very, very small. If you compare our specific equation for this experiment to the familiar y equals mx plus c, well, you'll see that if you put s on the y-axis, and if you put the time squared on the x-axis, that leaves an intercept equal to 0, in theory, and a gradient value equal to half of g. Example data might look like this. This is real data. You have your different heights you've chosen, you time it, about 5 times is good, and then you work out an average. You do this for every single setting. Once you've got all your averages, you then square them to work out t squared. If you were to plot just height against time, you get this curve. And the data does neatly follow a curve, right? That's fine. But it's very hard to tell from a curve if it's exact or not. So directly plotting height against t squared, that's following this equation, the mathematics predicts that that ought to be a straight line, and it is. And since we've got a release speed of 0, it should go through the origin, and it does. Finally, from the value of the gradient, sorry, that's a mistake there, from the value of the gradient, you can work out the value of g by doubling it. This is a slightly more advanced version of the same sheet as before. Again, I've done some extra sums up here to work out just how carefully we think we were when we actually worked out those values. You don't need to worry too much about this. It's just really to show off the quality of the equipment. But again, you find that it does